Let me go ahead and shut this off. Okay, so today we are going to be talking about the chi-square test for homogeneity. So everything from goodness of fit is going to kind of carry over. There are a couple of things we do slightly differently just because we're dealing with another sample of data, but a lot of the practices are the same. We are doing a version of phantoms. We are just not defining our parameter at the beginning, and we are still writing our hypotheses in terms of words and not variables and values. So, first thing, when do I use the test of homogeneity? So, it's going to be a test that is going to compare two or more groups. So, I have at least two samples and I'm comparing them on one categorical variable. So if you remember from our goodness of fit test, we were just comparing one population on one categorical variable. Now we're comparing two or more populations on one. So we are going to be in the realm of two-way tables. The only chi-square test that does have a one-way table is the goodness of fit test. So in this test, we are asking whether choices are going to be the same among different groups. So are we going to see the same proportions between group one and group two? Are they going to act in the same way? Now, there is no model that we are following. That's what goodness of fit is asking. Does the data follow a expected proportions? Are they equally distributed? All of that is from goodness of fit. We don't have a model. We are just comparing two groups together to see if they are the same. So when we're writing our hypotheses, we're going to be talking about the distribution of a categorical variable among our two groups is either going to be the same or it's going to be not the same. So the null is always that there is no difference, that they are equal to each other. So, more commonly than not, you will see it written as it is the same or it is not the same, but sometimes they like to throw in there is no difference just to confuse you. But most often you will see it written as the same or not the same. So, again, you are going to want to sprinkle in your context from the question in order to get credit for correctly writing your hypotheses. That's why I kind of have our categorical variable and two or more groups notated. Now, assumptions and conditions are going to work similarly to our chi-square test for goodness of fit. Again, yes, please verify that your data is counts. Otherwise, there's no point in even running a chi-square test because you're not dealing with categorical data. That is something you should be checking before you even begin once you make your initial decision of what test should I be doing. Now, the independence assumption is satisfied by checking the randomization condition, which we're very familiar with. Please make sure that you are checking it for both groups. So both populations that are selected, make sure that they're randomly selected. Now, 10% condition is going to make sure that you are sampling less than 10% of your population. And again, we are dealing with two populations, so we do check that 10% condition for all groups. And we do have our expected cell frequency counts condition, where we want to make sure we see at least 5 individuals in each cell. Now, something that's going to be a little different here is because we are dealing with two groups, a lot of the time, or I'd say about 50-50, we deal with questions where someone is imposing an experiment and they have treatments that they're assigning and they have volunteers that they're working with, and we can't necessarily assume that they've randomly selected their sample. So we are going to go back into the idea of if it is an experiment where you are assigning people to treatments, we can satisfy the randomization condition by randomly assigning treatments, and the 10% condition by saying we can assume independence among the individuals in the study. Basically, one person's results is not going to affect another person's results from the experiment. So when you are dealing with a problem that doesn't have just a random collection of data, instead they're actually doing an experiment, These two conditions can be replaced with random assignment of treatments and assuming independence among your samples. Now, we do have a different way to calculate expected frequencies. Before, it was just kind of follow along with what the proportions they expect are and multiply it by the sample size. Now we're dealing with two different populations on one variable. So the way that we calculate that is we're going to take the row total, so the row total number of samples, and the column total, and divide it by the table total. Now, I say this because there are times where in the multiple choice section, they will ask you, what is the expected count for dogs who are 5 years old? And you can just go straight to that cell, use this formula, churn it out very quickly. But if you are doing it in the test for homogeneity or eventually independence, it's time consuming, especially when you have multiple cells that you need to do this for. So, one thing I do want to note is this is something that can be done using the calculator. We're going to kind of work and use our calculator to our advantage just to save time in the eventuality that this might be an FRQ question that you don't want to calculate for every single expected count in a table. Now, again, remember in your condition. So we're going to do things a little backwards when we actually run the test, but in the condition, we have to state expected values. So we're going to kind of work in a weird zigzag line through our phantoms. So, name, chi-square test for homogeneity. Calculating the chi-square test, it is the same formula from goodness of fit. However, again, this is something that can be done using the calculator. I would advise you to do it in your calculator just because now that we're dealing with two-way tables, it was kind of long when we were dealing with one-way tables. Multiply it by 2. A long formula. Not worth the time and effort going into calculating it by hand. Now, degrees of freedom is going to change. And what's nice is the homogeneity and independence tests share the same calculation for degree of freedom. We are going to take the number of rows minus 1 and multiply it by the number of columns minus 1. And the rows are horizontal, columns are vertical, just a friendly reminder, and they will be based on the two-way table of observed counts. Now, one thing to note here especially is do not include the totals. Now, sometimes the tables will have a row and column of totals for you, which is usually nice because you don't have to total them up yourself. But in your counts for rows and columns, do not include that. Just include data. Collected counts, not the totals. Also, another thing with the calculator chi-square test, you do not have to enter a degree of freedom because you're technically giving them all of the data, the calculator. You're giving the calculator all of the data it needs to determine what degree of freedom is. So, yes, you can do it using the formula. However, your calculator will also do it for you on this test. So going into calculator steps, I'm going to go over this a little bit more once we get into a question. But basically, we're going to enter in observed values into matrix A. And then I'm going to tell you that we're leaving this matrix B, we're going to leave it blank because the calculator is going to auto-populate it for you. They're going to take all of your observed values and actually do the formula and calculate expected values for you. So, yes, you could go through and calculate them all. And yes, you can enter them and run the test, but you're going to get the same value someone who left it blank is going to get. So, save your time. Smarter, not harder. Now, once we run the test, it's going to say observed, expected. Basically, you're telling it where do I want to put my expected values. And we'll just usually typically put it in matrix B. Calculate, we're going to record the chi-squared, the p-value, and it's going to give you degree of freedom on this test. So again, it's going to generate expected values, degree of freedom, and I'll show you once we run through one how you can access and see the matrix. Typically, it's easiest to go through and go back to the edit menu of matrices, but you can actually type it in and enter. And don't forget to record them for your conditions. We'll kind of work in reverse once we get to that step. And one more note, it is going to ask you for row times columns before you can enter data. If your calculator is not updated where it does ask you that, let me know and we'll try to work something out to get your hands on a calculator that does have that option. Um, Conclusion is the same since our p-value of whatever is less or greater. We reject or fail to reject the null. There is or is not convincing evidence that the alternative hypothesis, remember, this is similar to what we did yesterday or 2 days ago, where we are going to be using the alternative hypothesis in our summary. It's the way they like it, it's the way they write it. We go with what is known. So let's go ahead and get started on one of these problems. Example 1, Andrea is addicted to TikTok, and she believes that most Richardson High School students are too. She wants to investigate if there is a difference in TikTok usage among juniors and seniors. And typically with our test for homogeneity, if there is a difference, is a good sign of us doing homogeneity over independence. Now, going to how do I decide between goodness of fit and homogeneity? I have a two-way table. I don't have just one row and multiple columns or one column and multiple rows. I have a two-way table. That already eliminates goodness of fit. Only other option is homogeneity. And she's trying to see it among juniors and seniors. She randomly samples 65 juniors and 85 seniors. The data she collected is given below. So we have her table, we have her totals, we have once a month, once a week, at least once a day. Now, is there convincing evidence of a difference in the distribution of TikTok usage among RHS juniors and seniors? So, my first step is going to be writing my hypotheses. So, I'm going to go ahead and write my null. The distribution of TikTok usage among RHS juniors and seniors is the same. So, remember, it's always the same for the null, and for the alternative, is the distribution not the same? And you could go in and say, is it different? I typically try to word it in a language where it's like opposites of each other. I think once you start mixing and matching words, things get a little confusing, but it is totally okay to say is different. Once we have our hypotheses written, we are going to go in and start checking our conditions. So the first two, again, you should be pretty familiar with. It does state that she randomly selected both samples. So that satisfies my randomness condition. Again, you want to verify it for both of the groups you're dealing with or more. Sometimes it's two, sometimes it's three. We're going to assume both. Assume at least 650 juniors, because that's 65 times 10, and 850 seniors, because that's 85 times 10, are at RHS. That is definitely reasonable. Maybe 850 seniors gets a little iffy. Maybe like at the top of the year, we have that many. Kind of drops down by the time we get to the end. Some people graduate early, some people transfer. We're just going to assume. If we include MPA, it's probably 850. Now, expected counts. So once you get into two-way tables, going through the model of drawing out the same table and filling it in with expected counts does get to be a little time consuming. And this is if you happen to get a chi-square test on an FRQ, it's not the one you want to spend a lot of time on. It's one that you want to get in, get out, be done. So with the two-way tables, we can enter in our data or write our expected values as a matrix. So I'm going to kind of outline mine for now. I have expected because it's going to EXP does signal for expected. They will know that on the AP exam. And I just have a blank matrix. Now, this is going to be kind of different from what we normally do. I don't want to go in and calculate expected values for 1, 2, 3, 4, 5, 6 cells. It's not super time consuming. Like, yes, it's doable, but I want to save time. So I'm going to hold off on this because even if this condition happened to fail, generally you are going to continue on with the test anyway. So I'm just going to hold off and I'm going to move on and I'm going to name my method, chi-square test for homogeneity. I know the spelling can be iffy. Try your very best. Most of you are probably typing, so hopefully spell check is your friend. Homogeneity, and I'm going to actually run the test. So I'm going to open my calculator and I'm going to walk you through the calculator steps for this. Now, I do want to briefly talk about what is our observed data. Remember, we're not going to include the totals. So my matrix A that I'm entering into my calculator is just the collected sample. So I have 1, 2, 3 rows and 1, 2 columns. So if I wanted to calculate degree of freedom by hand, I'm going to get 3 rows by 2 columns. Degree of freedom is 3 minus 1 times 2 minus 1, which should just be 2. This is not necessary because the calculator is going to do it for me, but if you wanted to, you could do it by hand. I think it's easier to do it by hand if it's just a multiple choice question and you're not running the full test anyway. So, gonna go and open my calculator. The first thing I'm going to want to do is put my observed data into matrix A. So I'm going to go to second and this X inverse button where I see matrix above it, and I'm going to go over to edit. And I'm going to edit matrix A. Now it's going to ask me how many rows and how many columns does my matrix have? Well, we said it was a 3 by 2. So I'm going to go ahead and type in my data for 10, 15, 21, 46, and 54. And once I have my data in my calculator, I can go straight to the test. So I'm going to go to Stat, over to Tests, and I'm going to go up, because it's easiest, to C, to chi-square test. We're not doing the GOF test anymore, just the chi-square test. And it's going to ask you, where are your observed values A? And it's going to say expected, but it's going to populate it for you. So just make sure you have it in the matrix that you want. Again, generally you're working with matrix A and matrix B. You never have to change these. So then I'm going to go down to calculate. And I'm going to hit enter. And I get my chi-squared value, I get my p-value, and I get my degree of freedom, which is 2. So it gives me everything I need. So I'm going to go ahead and record that for now. Chi-squared, p-value. I already have my degree of freedom written down, so I'm not going to write it down again, but it is there. Now, I still need to take care of this condition. I still need to fill in my expected values for my third condition. So I'm going to go back to my calculator. And I'm going to go to matrix again, so second matrix. Now you have a couple of options of how to get your matrix visible. And if you notice, now matrix 2, matrix B, is populated. You could go to edit and you could select 2, and then you can go in and you can hover over each cell and it has the counts, the expected counts there for you. So it's 6.06, 15.6, 14.3, 7.93, 20.4. That's one option. I think this is easier because you're able to see the full value. Another thing you could do is you could go to second matrix and you can just enter in B and press enter, and it's going to show up in your main menu. Usually this is okay when your matrix is easy to see. It's only 2 columns. Once you get to 3, you have to start scrolling. The calculator gets super weird about that. But Either way is okay. Now, for expected counts, I think it's okay to only round to like 2 decimal places or 1 decimal place. Um, I still round to 4 just because that's my habit. I think rounding to 4 decimal places is probably the best option. If you keep something consistent, you'll do it all of the time. But here are my expected counts filled in, and all of them are greater than or equal to 5. So most of the grunt work for the homogeneity test is done in the calculator. Now, could you do it by hand? Absolutely. Would it take a little bit longer? For sure. But you'd still get the same answers. So I do think using the calculator in these chi-square tests is probably your best option. I know a lot of us like to do the z-tests and stuff by hand. Those are more straightforward than these guys. So once I have my expected values written down, kind of working in reverse a little bit, I'm going to go ahead and summarize my conclusion. So my p is greater than 0.05. So I'm going to say, since our p-value of 0.4555 is greater than alpha, we fail to reject the null. There is not convincing evidence that the distribution of TikTok usage among RHS juniors and seniors is not the same. Another way, this is the one where it makes a little more sense if you changed it to difference, is there's not convincing evidence that they're different. But I think patterns work best, so we work in patterns. Going to give you a minute or two to finish copying things down. I know we kind of covered a lot very quickly in that last bit. Okay, we are going to go ahead and move on to example 2. I will, of course, post the filled in notes at the end of the day, so if you happen to miss something, don't worry about it, or I can even scroll back at the end of the lesson. But I will post these filled in notes at the end of the day. So, example 2. Aspirin prevents blood from clotting, which helps prevent strokes. A medical study asked whether adding another anti-clotting drug named dipridimol, I'm going to say that's the best pronunciation I can do, would be more effective for patients who already had a stroke. Here are the data on strokes during the 2 years of the study. Now, I know we did not get a lot of information from this question, from this prompt, but we did get one big key piece, and it's the fact that it is a medical study. Anytime you are told it is a medical study, or the study is printed in an academic journal, or one of the big polling organizations like Gallup um, does a poll, we generally are going to assume that those are well designed experiments and surveys. So we're going to assume that they're doing things the way they're supposed to, just because of the fact that it is a claimed medical study that is performing an experiment, because they are going to be changing the different treatments for different patients to see what's the best outcome. Now, this question is a little bit different because they don't organize the data for us. They want us to organize it ourselves. So they gave us 4 treatment groups with the specific treatments, how many patients were in the treatment group total, and how many had a stroke. So we need to summarize this data in a two-way table. And often things like this do show up on the AP exam just to see if you know how to process data and information. So there are a couple of things I know. I know the totals. I know the totals for each treatment group, and I know how many people had a stroke in each of those treatment groups. So I'm going to fill in those values first. Placebos was 1649, 250 had a stroke. Aspirin 1649, 206 had a stroke. 1654, 211. 1650, 157. Now, from here, it's just subtraction. I know how many had a stroke. I know how many there were total. I'm just going to subtract those two numbers to get how many people didn't have a stroke. So I'm going to go in and I'm going to do the subtractions. In the placebo group, 1,399 didn't. Aspirin had 1,443. Same thing with our dipridimol. And for 1,493 in both had both did not have a stroke. And I did go ahead and fill in my totals for the stroke, no stroke total number of people in the experiment. Total columns aren't always necessary. Really, the only use for them is when you are doing the expected counts by hand. That makes it very easy. If you're going to be doing it solely in your calculator, you don't really have to have total columns because you don't use it for anything other than figuring out expected counts. So once I get my data summarized, I am going to go in and I'm going to write my hypotheses. So I have the distribution of patients. Another thing that they like to change with distribution is the proportion. So if that said proportion instead, it would mean the same thing. The distribution of patients who have a stroke among the 4 treatments is the same, or the distribution of patients who have a stroke among the 4 treatments is not the same. Again, the null is always that they are the same. Now, with us doing an experiment, our conditions are going to look a little bit different because, again, we don't necessarily have the capability of telling someone, hey, you're volunteering for an experiment, just so you know. You're taking part in my experiment. We have to deal with volunteers. So because of that, we have to work a little bit differently. And because we're going to assume that this is a well-designed experiment because it is a medical study, I'm going to say that the treatment groups were randomly assigned. And I put a little note next to it that said medical study, not that that would be something that you would have to do on the AP exam. They can infer from the question that that's kind of what we're going to assume based on the information given. And we're going to assume that the patient results are independent, meaning one patient resulting in a stroke does not necessarily mean another patient is going to result in a stroke. Each person is independent. Now, again, with our third condition, I'm not going to fill it in quite yet, only because I want my calculator to do the work for me. However, I do always put something there so I don't forget to come back and do it. Trust me, happens all the time. I always suggest just filling it in at the end. So I'm going to go ahead and move on to actually performing the test. Going to name it chi-square test for homogeneity, wherever it may be. There we go. And I'm going to determine what needs to go into my matrix. So I'm going to come back to my data and I'm going to see, well, remember, total columns do not matter. So the matrix that I'm going to be entering into my calculator is going to be just the counts, just my stroke, no stroke, placebo, aspirin, dipridimol, and both. That is going to be it. So it's going to be a 2-row by 4-column matrix. So let's go ahead and get that taken care of. I'm going to open my calculator. Let's see. And I'm going to go to second, x inverse. Now, I have already populated matrix C with the values. So it's a 2 by 4 matrix, and I plugged in my results for stroke, and I plugged in my results for no stroke. And once I have my matrix in there, I'm not going to, you probably put it in matrix A. That is okay. I'm going to change it just for the sake of time. I'm going to tell my calculator to run the chi-square test on matrix C and matrix D just to have it in those positions. So I'm going to go to stat, over to tests, up to chi-square tests, which is C, and I'm going to change mine. You don't have to change yours if you plugged it into matrix A to, oh gosh, can't remember how to do it now. Let's see. I think I just go to matrix. There we go. And I'm going to change this to matrix D, and I'm going to calculate. So if you do happen to change it, all you have to do is hover over where the matrix is and just do second x inverse, enter, with whatever matrix you're interested in. So my chi-squared value is 24.2428. My p-value is very, very, very small. Please always remember to check the end of your p-value, because if you have this notation here, it means I need to move my decimal place to the left 5 times. And I have my degree of freedom. So, gonna write that in. Chi-squared is equal to 24.2428. I went ahead and wrote the 2. I went 5 decimal places on this one only because I generally like to have a number there if one is showing. If it's like to the negative 25, I'm going to assume that's essentially 0. If you said this was essentially 0, it would be acceptable. Degree of freedom is 3. Now, before I go on into my conclusion, I am going to fill in my expected values. So I'm going to go back to my calculator, going to go to second matrix, over to edit, and I'm going to go down to matrix D. And I can go in and I can hover over each value to get the calculated expected value. So you'll want to write down all 8 of them, and all 8 of them are larger than 5. So I can satisfy my condition. Once that is done, I go in and I conclude. Since the p-value of essentially 0.00002 is less than alpha, we reject the null. This is one of the first ones that we've rejected for chi-squared. There is convincing evidence that the distribution of patients who have a stroke among the 4 treatments is not the same. Now, we can't necessarily make the conclusion of one is actually doing its job, because we don't really have cause and effect unless we're like in a completely enclosed environment where we know all of the controls. And yes, this is a medical study, so we can assume it's doing what it's supposed to, but I wouldn't draw that conclusion here just because I don't know for sure. But we can say, based on what we know, the distribution is not the same. Once you are finished writing this down, you will have a MyLab assignment posted for 8.2 that follows along with the chi-square test for homogeneity. One note that I did want to make is if you did not do 8.1, it's due at 11:59 tonight, and we will have a quiz open this afternoon at 4:20. It closes next Wednesday at 11:59. So we do have a quiz for this unit. One more lesson for this unit, actually. It's a very short one. We're just going to do our chi-square test for independence, and then we will review and test again. We're almost done with Unit 8.